So some more reactions. So our next subsection E, we're going to talk about addition of hydrogen halides. Okay, so in this, so I'm going to use a terminal triple bond so you guys can see Markovnikov's rule in action. Okay, so this does follow Markovnikov's rule just like it did in double bonds when we add a hydrogen halide across a double bond. Okay, so it's the exact same mechanism as before. Okay, so we're going to take our pi bond, it's going to attack a hydrogen, leaving group's going to leave. We want the positive charge to go on the more substituted carbon, which is going to be this carbon here, which means this carbon is going to get the hydrogen. Okay, so with the first equivalent, we're going to have the hydrogen add to the carbon that already has the most amount of hydrogens, and then we get our halogen added to where the carbocation is, the more substituted carbon. If we add another equivalent, it's going to add the same way. It's still going to follow Markovnikov's rule. So we get two halogens on this carbon here, and then we get two hydrogens added to this carbon here, the terminal alkyne. So this follows Markovnikov's rule still. Okay. And so let's just do, the mechanism. Again, it's the same mechanism as before. Excuse me. So if you have your hydrogen halide, the pi bond is going to attack the hydrogen and the leaving group is going to leave SN2. And that's going to form a carbocation on our more substituted carbon because the hydrogen is going to get added to the least substituted. And again, this is still linear, okay? So this our leaving group that left, when it comes back to attack, it can attack any which way. So, this is both syn and anti-addition again. No matter which hydrogen gets added, it's going to do both syn and anti-addition. So you have this vinyl carbocation. This is very short-lived. It's pretty unstable, but it can still happen. So this is the fast part of the reaction. This guy here is our rate determining step. And we will get both syn and anti-addition here. So I'll say the vinyl carbocation is short-lived, and you get both syn and anti-addition. Okay. So next let's do, and then again, it's the same mechanism as before if you add the second equivalent of HBr, okay, or, your hydrogen halide. Same mechanism as you did with double bonds, okay? You guys already know that. I don't have to go through it again. Okay, so next we're going to do hydration of alkynes, okay? Again, just moving down the line of reactions that you guys learned in Chapter 8. Hydration of alkynes. And so these hydration reactions, though, they're not going to form diols, okay, like you would expect. They actually form ketones and aldehydes. And you're like, what? Ketones and aldehydes? How does this happen? I know, Ricky and Stripes, they're also thinking like, what's going on here? So I will totally clue you guys in. So hydration of alkynes to ketones and aldehydes. Okay, so the generic reaction, if you were to have a terminal triple bond, and if you were to react it with water, and if you were to use, in the same reaction conditions, so H2 SO4, so our sulfuric acid, super strong acid, you would expect that you're going to form, first we form, water adding across that double bond, following Markovnikov's rule. And so, this is our Markovnikov product for the first addition, okay? However, this is called an enol, okay? So enols, they're very short-lived, okay? So the name enol, it comes from ene as in alkene, because you have a double bond here, and ol from alcohol, okay? So an enol is an alcohol on an alkene, okay? They're very short-lived, and in the presence of acid or base, they do what's called tautomerization. I know that's a mouthful, okay? But what happens is it's this equilibrium, and so it's, heavily favored the keto form. And so what that looks like is this guy here, okay? So the only difference between these two is that, is the placement of the pi electrons. So here you have pi electrons between these two carbons. Here you have the pi electrons between these two carbons. And then the placement of this hydrogen. Here it's on the oxygen. Here it's on this carbon over here, okay? So these are a special type of constitutional isomers called tautomers, okay? And this is going to lead us, and I'm going to show you guys how this actually works. I'm also going to specify that this is our Markovnikov addition product. So it's going to, this is our Markovnikov reaction when we learned it with double bonds. So this still is going to follow Markovnikov's rule, adding the alcohol to the more substituted carbon. But now I'm going to show you guys the mechanism for this tautomerization. So, keto, this is called keto enol to tautomerism. I know that's a mouthful and a tongue twister. But what a tautomer, and I always call it tautomerization, because that's easier to pronounce, I guess. I don't know. But this is a equilibrium reaction, or just an equilibrium, we'll say. And the reason that, this happens is because a carbonyl is going to be more stable, or is more stable, than a carbon-carbon double bond. Okay? So, again, this is the difference between the placement of a double bond and the placement of a hydrogen. So this is going to be our enol product, and it's an equilibrium, and this would be the keto form. So it's the placement of this hydrogen here and this pi bond. Okay, that's the only difference. So this is the enol, this is the keto. Keto just comes from, ketone, which is, the carbonyl. But if that was a hydrogen, it would be an aldehyde, but we would still call it the keto product in this enol keto tautomerization, okay? And, before I show you guys how to do the mechanism, I first want to show you guys that this, so we just showed you the Markovnikov addition. So now let's do the anti-Markovnikov addition. So it's the same, again, reaction conditions of adding water across the double bond. So we have So the anti-Markovnikov product is the hydroboration oxidation. Okay. So if we were to have our terminal triple bond, and you react it with BH3, so remember that's going to add the boron onto the least substituted carbon, and the hydrogen onto the more substituted carbon, and then with in the presence of H2O2 and base, you are going to replace that BH2 with an alcohol. So that is going to form our enol. But now our enol, the alcohol, is now on the terminal carbon instead of being on on the more substituted. So this is our anti-Markovnikov product. It's still going to tautomerize though, okay? So it's still going to have this equilibrium, but now it's in the presence of base, because in this reaction we have base. So in the presence of base, we're just going to form a keto here, a carbonyl. We still have that hydrogen there. Then we have this carbon here, and we have that R group, and we have this hydrogen here, but now that hydrogen moves over to this carbon here. Okay, so now we're forming an aldehyde. This is still called, so this is our enol product. This is still called our this is still called the keto product. Okay, and so if you were to react a terminal alkyne with our hydroboration oxidation, your final product is going to be the keto form. Same with when we do our hydration of alkenes. So with H2 and acid, you're still going to get the keto form as your final product. Okay? So now let's go through these mechanisms. Okay? So there's two different mechanisms. One is with acid and one is with base, because in acidic conditions, we have, the Markovnikov addition. And then in basic conditions, we have the anti-Markovnikov addition, okay? And remember, in acidic conditions, you are never going to have a negative charge. And in basic conditions, you are never going to have a positive charge. So let's, I'm going to start a new piece of paper to go through these mechanisms, okay?